A landmine or a bottle top. It's very easy to tell the difference when you can see them. However, when they're buried in the ground, how do you tell which is a dangerous item that can injure or even kill someone, and which is a harmless clutter like a bottle top? This is just one of the problems we face when researching landmine detection. I'm Professor Tony Payton, and I work on landmine detection research at the University of Manchester. This talk is landmine or bottle top. Could you tell the difference? It's fairly obvious why we need to tell the difference when trying to detect landmines, but how many of us, when thinking about landmine detection, would have thought about the other items in the ground and the problems involved when you try to differentiate between a threat item and harmless clutter? For people who have to live in mine-affected areas, the presence of landmines and unexploded ordnance continue to threaten lives on a daily basis. In 2019, over 5,000 people were injured or killed due to landmines or other explosive remnants of war. For deminers who must detect and remove landmines, digging up every metal item can be very laborious. This is because it can take at least 15 minutes to carefully excavate each metal detector alarm in order to determine whether it is a mine or not. However, if harmless clutter such as a bottle top can be identified at the point of detection, then these innocuous items can be rapidly removed mechanically, which then allows the deminer to focus on serious threats. In some minefields, for every landmine detected, there can be over 100 times more false positive alarms caused by innocuous metallic clutter. That's the background. Now let's consider the challenges and how science, engineering and maths can be applied to identify what's buried in the ground. This poses some very interesting and challenging scientific questions, which I'd like to tell you about in this short lecture. Our landmine detection research can be split into three areas. Metal detection and characterization. Can we be sure it's a harmless metallic clutter, or is it a threat item? Ground penetrating radar. What if the device has very little metal in it? Sensor fusion, dual mode and even multi-mode sensor systems, radar plus metal detection. Also other sensors, and particularly the possibilities for position-enabled detectors. So to understand the science behind metal detection and move from basic metal detection to metal characterization, there are three things that we need to know. The first is to understand the response of the target threat item. The second is to understand the response of innocuous items. The third is to understand the response of the ground. Let's take these one by one. We need to know the response of metal items that are commonly found in landmines. And I have two examples here. On the right is an old Soviet PMM, dating back to the late 1950s and widely deployed in many conflicts since. You can see it contains a variety of metal components, springs, etc. On the left is an American M14, similar age and also widely deployed. Again, you can see it has a variety of similar metal components which give a particular electromagnetic signature. Here is an innocuous bottle top. Different type of metal, different shape and different size. Note also the direction of the metal piece also is important. For instance, the response in this direction is very different to the response here. And note the symmetry. So we have to account for this three-dimensional response. The differences between the mines and the innocuous metal are obvious to us visually, but they also show significance electromagnetically. Turning to the ground, this can also provide a confounding signal and can be what is known as uncooperative, particularly if it contains magnetic mineralization. In fact, in some iron-rich areas, the response from the ground can be very uncooperative, masking the signal from these types of metal components. So discriminating between the ground and the target is a key challenge. Therefore, our problem is to understand the response of the threat items, innocuous clutter items and the ground, so that we can determine or recognise their three-dimensional signatures with sufficient precision in real time. The signatures are also frequency dependent, which is a parameter we have some freedom over. Ultimately, this problem involves a solution to some challenging mathematical tasks, fast computation, and borrow some ideas from machine learning. We've looked at the metal content, but of course some threats have very little metal. So what about the rest of the device? So to deal with the non-conducting parts, e.g. the plastic case, the explosive charge inside, we use a special type of radar, known as ground penetrating radar, commonly referred to as GPR. This is designed to operate very close to the target and involves the use of ultra-wideband electromagnetic signals, typically from 100 megahertz to around 5 gigahertz. This is in contrast to metal detection, which operates from a few kilohertz to 100 kilohertz. You may notice that there's a gap in the frequency spectrum that's not currently used, from 100 kilohertz to 100 megahertz, which is subject to recent research, particularly in the US. Previously, it has been too difficult to make sense of the signals in this range, but recent advances in computer modelling, AI, and signal processing are changing that. I will just talk about 3 of the challenges of GPR. The first is, how do we detect and distinguish the signature from the threat objects with benign objects and the ground? This has similarities with metal detection that we have just discussed. The second is how to make very short pulses so that we can distinguish very close targets, such as mines that are buried almost flush with the surface of the ground. This is because we're using the echo from the target. So if the target is very close, the signal has to be very short. Otherwise, the transmitted and received pulses will overlap. The third challenge with GPR is, how do we remove the echo from the ground and other spurious echoes? Recent research is looking at how to use GPR at greater distances from the ground for use from drones and other aerial vehicles. Now we've looked at metal detection and GPR. Naturally, it makes sense to combine both sets of data to maximise the probability of detection and minimise the false alarm rate. There is other data that we could use and fuse together, such as position. This is because it's now possible to measure the position of the detector head in real time to centimetre precision as a deminer is using the device. This allows us to produce maps of the detected signal, showing hotspots over the ground, such as the one shown here. Of course, such maps are of limited use to the deminers while they are scanning, as they have to concentrate on scanning the detector over the ground. The deminers want a much simpler binary output: a threat, innocuous, or nothing detected. However, a heat map is just the start of the data we have. At each position, we have the echo response of the radar and the multi-frequency metal detector signals. With position, this potentially is a wealth of information. Could be fed into a more sophisticated discrimination algorithm to output whether we have a threat or an innocuous item, which is what the deminer needs to know. The data can also be recorded and used to improve and manage the process. I hope you found this lightning lecture interesting, and I hope it has given you insight into the latest science and the research that is used for challenging applications like landmine detection, which is just one critical part of the demining process. We are very grateful to the Sir Bobby Charlton Foundation for their generous and sustained support of this research over the past decade. Over the years, Sir Bobby has been a regular visitor to our labs, and the charity has helped very practically with visits to minefields, test sites, and partnership with a detector manufacturer. I'm also very grateful to the Royal Society for the opportunity to talk about the research. This is just one of the applications of electromagnetic sensing that we work on at Manchester. We also apply similar techniques to many diverse applications: medical, agricultural, industrial inspection, security screening. These are all areas of active research, so please check out our website. I would also like to leave you with a final thought. Next time you open a bottle, take a second to think about the challenging work that deminers do as they work in very difficult conditions. And please have a look at the Landmine Free 2025 website. Thank you.